In lecture 22, we talked about the average rate of change. And if you haven't, you were not in class or you did not watch that lesson or that lecture, please go and recheck it again, because today I want us to talk about instantaneous rate of change and look at what are the differences between the average rate of change and instantaneous rate of change, or just the rate of change at a particular point, not between 2 points. Okay, so when we're doing with the average rate of change, we said that what we need 2 points, 1 point on the curve and the other point on the curve. Suppose this one is our curve f, and then if we are looking for the average rate of change of this function between these 2 points, we are actually looking at the slope of this straight line that is passing through these 2 points, or we're actually looking for the gradient of this line that is passing through these particular 2 points. So if we are looking for that slope or the gradient of that line, we usually say m, which is the slope or the gradient, is equal to y2 minus y1 all over x2 minus x1. So if we have y1 here, we must have x1 here, and y2 goes with x2. You can change this and start with these two and end with these two, but what is important is that if this one is we are starting with y1, make sure that you are starting by x1 in the denominator. And then we said that actually if we don't have x1 and x2, we can say that this is actually the same as, if you look into this point here, which is going to be our y2, we can say that it is f of x2. F of x2 minus f of x1, and then in the denominator you end up having x2 minus x1. So that was our summary of lecture 22. Now this one here, we call it the average rate of change of this function f between these 2 points. Now the kicker is here. If let's say, now I still have the same function f, but I wanted to find the average slope of this line here, or the slope of this tangent line that is touching this curve here at this particular point. Let me say it again. Suppose I want the slope of the straight line that is touching this curve at this particular point. Only once it's going to touch it here. Or the slope of the tangent line touching this curve at this point here, where x is equal to a. How can I actually find the slope? So the slope of this curve that is touching that once, we usually say that it is the rate of change of this function at that point. So it is the rate of change of this function at that point, or we usually say it is an instantaneous rate of change of this function at this particular point. I hope you can see the difference here, because what we're actually saying this side, average means you need 2 points on the function. We have 2 points on the function. Instantaneous means that you have only 1 point on the function. So this particular line here is touching that curve at that particular point once. But if you look into this line here, it's touching here and there. Of course, if we continue, it's going to touch even there. But what is important here, we have 2 points, and here we have only 1 point. That is actually the main difference between these two. Another thing we talked about, we said that if the slope or the gradient is greater than 0, then this line here is saying that we have an increase. So if it's greater than 0, we have actually an increase. But if it is less than 0, then this function should be going all the way like this, so we have a decrease. The third thing that is important here is that if I have 2 lines, I have another line here that is like this, such that this line here and that line are parallel. If these two lines are parallel, then their slopes are equal. That's what is important. Let me repeat it. The slope of two lines that are parallel is the same. So they have the same gradient. Okay. Now, one way to actually find the slope at this particular point here of this line is very easy, because now we know that the slope of this line and that line is the same if they are parallel, is to find a line that is going to pass through one point here. Let me move this out. Pass through a point here and a point there. Both of these 2 points are on the curve, and that line is parallel to that. So if we can find that line, then we'll be able to find the slope of this this line here, because it will be parallel to that line. So that's what we're gonna do here. So let me actually try and plot another plot here. This is bad plot. Let me try and plot this one here. Right. These are the y-axis, these are the x-axis. I'm going to put in some arrows to say that we're continuing all the way. Now, I am saying that if, let's say, we have a curve, this is our nice curve, and we have a tangent line that is supposed to pass through that point only once, right? So this is our tangent line. And this point here is the point we're calling point x is equal to a. Let me remove that. Right. And this is my function f. Of course, this is the straight line that is going all the way and all the way. Right. So this point here, if you look close to it, this point is on this curve f. So that point is supposed to be f of a. So if I'm plugging a here, I'm supposed to get the output here. I can simply say that when x is equal to a, y is f of a. This is this point there. Now, how can I actually find the slope of this line here? The slope of this line, we can find it by saying, I am going to pick some point here, right? This point here, I'm going to call it some value, right? And I'm going to pick another point somewhere there, such that the difference between these 2 points, I'm going to call it delta x, between this point up to a and this point up to there, I'm going to call it delta x. Now, the difference between this point and that is the same as the difference between this point and that point. So I pick these 2 points here. 1 point is there, 1 point is there. And this point here, the reason I'm not placing anything here, I want to call this point just some x because it's on the x-axis. And of course, this point, I can just say it is just some x. You will see why I'm just putting this instead of b1, b2. I don't want to do that. Now, and then the next thing that I want here, I want to draw a line that is going to pass through this point and that point, such that these 2 lines are parallel. If you look into this point is on f, this point is on f. Now, I have 2 points on the function, which means I can find the gradient of this line. Because this line and that line are parallel, then the gradient will be the same. So that's what we actually do here. Now, let us take an example here and see if how would this particular thing here actually work. Right. So basically, suppose that I have my function, and my function actually, let's say I have this example here. Given the function f such that whenever x is equal to 1, f of x is 1. Whenever x is equal to 2, f of 2 is 4. Whenever x is equal to 3, f of x is equal to 9, and so forth. And the question is, find the slope of the curve f at p at this point P, where x is equal to 2 and y is equal to 4. Remember that here we are only looking for the slope of the tangent line that is going to pass through this point here. We don't care if this line is either negative, is having a slope positive or negative. What we care about is here, we wanted to find the tangent line that is only going to touch this curve once at this particular point here. Another alternative way of asking this, even though these two means the same, would be approximate the slope of the curve f at this point. They're saying approximate, right? So we're gonna look at both these two questions and answer them in the same way that I'm still trying to actually explain here. So the first way to find the slope of this tangent line that is touching here is to find the slope of this line here, because they are parallel means same slope. Now, what I also wanted to find out, when I'm picking a point must be on the left, the point must be delta x away from this point here. And also on the right, the difference must be delta x away. So if you look into this particular table here, we wanted to find out what is the slope that is passing through of the line that is passing through here. So I need to choose one point on the left. The point that I'm going to choose is this one on the left. As you can see, the difference between 2 and 1 is 1. And I'm going to pick another point on the right, which is 3. As you can see, the difference between 3 and 2 is 1. So because of these two, I'm going to take this point and that point and actually find the gradient, right? So let me put this aside. So what we are actually saying now in that table, let me just try and place the table here. Maybe it's going to make sense here. So we had x and we had f of x here. Whenever x was 1, f of x was 1. Whenever x was 2, f of x was 4. And then we have 3 and 9. And then we have 4 and 16. Now, according to what I'm saying here is that we need a line that is parallel to that, or 2 points. So the gradient or the slope of this line is equal to the slope of this line. In other words, I'm going to pick this one here. This is the point of interest. So I want to pick that point on the left and that point on the right. And if you look carefully into that, I'm going to call this one here is going to be x1. So my x1 and y1 will be something like, whenever x is 1, y is equal to 1. And then I'm going to pick this one as x2 and y2. Whenever x is 3, y is equal to 9. So if you look at the slope of this line here, or the line that is passing through this point and that point, but not this one in the middle, it's going to be y2 minus y1 divided by x2 minus x1. So if you look carefully into this, you will end up having 9 minus 1 all over 3 minus 1, which is 8 over 2, which is 4. So the slope of the line that is passing through this point is going to be 8 over 2, which is equal to a 4. Right. So the slope of this is just going to be a 4. Now, if you look carefully into this, we have the slope of this line, which is equal to that. Is there any other way that we can actually get a slope of this line without actually looking at what is happening with the line that is parallel with that? So basically, another way to look into this is this. We want to end up including this point here. So if we wanted to include this point, there is no way that we can find a slope of the line that is passing through only these points, because this point and that point does not include that point. So another way to look at the slope of this is this. If I were to draw a line here that is going to pass through this point and that point there, we can see that this line is passing through this point. Let me use a different color here. Maybe it's going to make perfect sense now. So if I am picking a line that is going to pass through this point and that point, what is happening now, we can see that this line here is actually running faster than that line, so it's increasing faster than this line. So there's no way that this line can actually have the same slope as that. But now here's the kicker. If I draw the second line to pass through these 2 points, this is not a good one. If I draw a second line that is going to pass through this point and that point there, this line here is actually decreasing so faster than our line of interest here. So there is no way that this point, this line, the slope of this line and that line will be the same. But this one is increasing so faster and this one is decreasing so faster, such that if I were to take the slope of this line and the slope of this line and average them, I will get the slope of this line here, which is parallel to that line. So I need to find the slope of this line here and the slope of this line here so that I can add them and then divide by 2. I will be able to get the slope of that line there. So that's the second way of actually looking into it. What am I saying here? I am saying that this slope here, I'm going to call these 2 lines. This one I'm going to call it line 1, and then this red one I'm going to call it line 2. So if I were to take the slope of line 1, I add the slope of line 2, and then I divide by 2, I should be able to get the slope of the line that is in between these two. Bear in mind that the difference from this point to that point and the difference from this point to that point is the same, so that the average is not so different from the slope of that, the slope of this line. So this line and that line will give me the slope of this line. So basically, how can we find the slope of line 1? Let's go back here in our example. Our example was saying that we want to pass through this point here. So first I'm going to look for the line that is passing from this point and that point. And then look for the second line that is passing from this point and that point. And then I add these 2 slopes and then I divide by 2. So I'm still gonna say I had 1, 1, 2, 4, 3, 9, 4, and 16. That's what was happening here. And then on the numerator I had x, on the denominator I had y's. So first I'm gonna deal with this block here because this was the point of interest, so it needs to be included. So y is on the denominator here. So I'm going to take these ones as x1, y1, and then this one I'm going to take it as x2, y2. Now, this one here is going to be my y2. Remember that I have y2 minus y1 divided by x2 minus x1. So this is going to be, y2 is going to be 4 minus 1. So this one here is going to be 4 minus 1. And then we come to x, and then we're going to have 2 minus 1. So if you look into here, 4 minus 1 is going to be 3, and then 2 minus 1 is going to be 1, and this is just 3. And if we look for the second line here, the second line here is going to be this block here, this side. So my y2 is going to be 9 this time around. I'm going to have 9 minus, and then here we'll have a 4 as a y1, 4, and then this one is going to be 3 here, and then this one is going to be 2. 9 minus 4 is going to be 5. 3 minus 2 is going to be 1, which is the same as 5. Now, if I am taking now my m to be m1 plus m2 all over 2 is going to be 3 plus 5 over 2, which is the same as 3 plus 5 is going to be 8 over 2. So this is going to be a 4, which is actually the same as this one here. So basically, how do we end up finding the slope of the tangent line touching only at that point? We find it in two ways. The first one is find 2 points that are at the same distance away from A, and then those points, you take a line that is going to pass through those 2 points, and then you find the slope of that line, and then you would be able to get the slope of the line that will be parallel to that. Or you can just pick 2 points, but join this point of interest with that point, this point of interest with that point, have 2 lines, find the slope of that line, find the slope of the second line, and then after that, this is supposed to be you add them and then you divide by 2. This is supposed to be an approximation of this particular slope here. So just in a nutshell, when we're looking for the slope of this, or trying to a slope of the line passing through this point, we could just use this point here as x1, y1, and then this one here x2 and y2, and then find the slope of the line passing through this point and that point. That would be a good approximation. The second one is find the slope of the line passing through this point and that point, and then put it aside the slope of that, find the slope of the line passing through this point and that point, and then take those 2 slopes, add them, divide by 2, you get the good approximation of the slope that is passing through this particular point here. Now, let's look into this, because I want us to actually look into these questions. We have answered example 1. Now, I want us to find the slope of the curve f of x is equal to x squared at this point, and find the speed of this, and find this example here. Again, pause this video at this point, copy these questions, example 1, example 2, example 3, and then example 4. And then after that, you have copied them, you can continue with the video and then see how we do it, or do it and then fast forward the video to the point of your interest. Now, let's go back to what I was saying here. If you look carefully to this, when I was saying to you that plot a curve, I'm going to make this plot so big, right? Make a curve. This is going to be your curve. You want a slope of the line that is passing through, a slope of the line that is passing, this is bad, the slope of the line of the tangent line touching this curve once only at that point. Where this point here, I would say this point here down there, and then I know this point here. Okay, let me make this like this. Yeah, up to that point, I know that this point here is going to be my A. Of course, if this is F, then this point here is supposed to be F of A, right? If I want the slope of that, all I need to do is pick a point here. I'm going to pick a point somewhere here on the left, right? Pick a point somewhere on the left here, and just some X there. And a point on the right here, and then this point here, I'm going to call it, this is also going to be my X there. Now, I draw a line and then find the slope of this, and then as long as this distance here from A is delta is the same on both sides, I'll get a good approximation. Now, we don't really want an approximation. Suppose we want to make sure that our approximation is so good such that even the computer cannot pick the difference between the right slope and this approximation. So basically here, if I choose a point here, right? And draw a line that is passing through here, and draw another line that is passing through here. The line that I will get that is passing through here is not really, we are not really sure if it is going to be parallel, or what will be the difference between the slope of the line that is passing through these 2 points. But if you look here, we just assumed that if we take this, we're going to get that, okay, sure. But this way of doing two things, when we're picking the points, it might happen that I have a point, the point that I picked both on the right and on the left, they are not actually giving me a line that is parallel to that. Now, how can I make sure that the line that I will get will be parallel to that? So basically, I'm going to end up having a point that is like this. I choose a point that is going to be so close here on the curve, such that my x is going to be so close to A. And if you look into this, if I pick this point here, when I am drawing the line that is going to pass through, let me do this again. This one, I pick a point on the left so close to this point, such that even the computer cannot pick the difference between this point and that point. And I pick a point here on the left, just so close to this point, such that my x is so close here on the left. So the difference is so small between A and this point here on the right, and between A and this point on the left, such that if I am drawing now a line that is going to pass through these points, is going to be overlapping. Let me do this. It's going to be a line that is going, let me try and make sure it passes through there. As you can see, if I'm trying to pick a point there and a point there, this green line here is falling exactly on top of that line here, which is what I wanted, because now they are actually parallel. So I pick a point that is so close to that point, and a point on the left that is so close, such that when I'm trying to draw the line between these two points, the line is actually overlapping on top of these 2 points, and also on top of the line, right? I pick the point so close on the right, point so close on the left, such that the difference cannot be seen between this point X and A, this point X on the left and A. Now, how can I say that mathematically, that I've picked 2 points that are so close, right? What we actually say, I will do it, I will say it, I will write it in a moment. That was the first way of actually doing this, so that we find a line, pick 2 points that are so close to A, so that these 2 points, when I'm joining them, I get a line that is parallel to the tangent line. The second way was, I wanted to draw one line that is going to pass through this point here. Let me do this like this. So this point here, I'm going to write it in a red. This point here, I'm going to say, this point here on the right, I'm going to say I have x 3 and y 3. And then this one on the left, I'm going to say I have x2, and then I have y2. So I have these 2 points. So if you look into this point here and that point, you will notice that when I'm trying to draw a line that is going to pass through this point and that point in the middle there, the line that I will end up getting here will be, let me try and pass through that point. I'm trying to pass through this point. So the line that is passing through this point and that point is actually going straight on top of these other 2 functions. Can you see it? So it's going to pass through these 2 points. And if I'm looking now at the line that is going to pass through this point on the left and that point on the middle there, is going to pass like this and is also going to overlap with that line and go all the way down. Now, these two lines, what this means, the green one, I'm gonna call it the second line, and then this one here, the blue one, I'm gonna call it, the blue one is the third line. Now, if I am looking for the slope of the second line, because these lines overlap on top of that, you will find out the slope of the second line is the same as the slope of the first line. Now, if I want to find the slope of the tangent line, I just need to take m1 plus m2 and then I divide it by 2 like I did earlier on. Right. And if you look carefully into this, I will end up having, because m2 is the same as m1, I will end up having 2 times m1 divided by 2, right? Or simply 2 divided by 2 is just 1, so I'll end up having m1. So my slope of the tangent line is just the same as the slope of no, this was supposed to be the third line, 3. So this one was supposed to be 3, this was supposed to be 2, this was supposed to be 2, so that I end up saying I have 2. So this slope of the tangent line is the same as the slope of the second line. Now, how can we find the slope of either this green line or the blue line? All we need to do, we need to say that our slope is just the same as, I'm gonna take a point on the curve that is so close to the point that belongs to A. So I pick a point on the left, and then on the right, I pick an output that is up there, that is so close that the difference cannot be found, right? And also here, I pick the slope, I pick the point on the left, and then I go all the way up such that that point is so close to this point here on the curve. Now, what do we say by saying I pick a point so close? The limit as that x approaches A, right? Now, what is the actual slope of that line here? It means that I need to have my y2 minus y1 all over x minus x2 minus x1. If you look carefully into this, I still have x approaches A, and then here, what is basically happening here is that, remember that when I'm dealing with m1 or m2, one point is going to be this point x here, this point A here, and the output is going to be f of A. And then the other point here will be just x either on the left or on the right, and then I go and get the output. So here, if my y2 belongs to, let me write it like this here, my x2 here is just the point that I pick on the left or on the right. And then I plug it in the function, which is going to be my f of x. So I'm plugging this x there, and then I get my y2, and then my y1 is going to be the output of A, and then I subtract an A. So this is going to be the second definition of the slope, right? So this one is the instantaneous rate of change at that point. Because we pick this point so close that the computer cannot actually pick out the error or the difference, then this one becomes the exact slope at point x is equal to A. Let's see some examples here. Suppose I'm gonna do these examples using this. I hope that you actually captured the content, because that's what is important. The examples are so easy, are so damn easy. Let me look into these examples here. Let's look at example 2. Find the slope of the curve f of x at this point here. Right. So basically here, what is actually happening here is this. So we have, in this example here, we have our own example. Let me use red. We have our own example here. The example is saying we have f of x, and our f of x is equal to x squared. Now, I want to find the slope of the tangent line passing through this point, 2, 4. So if I'm plugging in 2 here, the output is 4. That's the meaning of that point there. This point must be here. Now, the slope that is passing through that point is going to be m, which is equal to the limit as x approaches a. But now, not only a, because the point is given as 2, so as x approaches 2. And then here, I'm going to have f of x. F of x is given as x squared minus, right, f of a. So if I take this 2 and plug it in here, what is the output? The output is going to be 2 squared is going to be 4, which is what was given. So I will end up having a 4 here. And then I divide this. The x is still there, and then minus, and then I have an a, which is in this case is a 2. Now, remember, the point x here, we were picking so close to 2, but it's not the exactly as 2. So we cannot say that this whole thing is not defined at 2, because what we are actually trying to do here, we are picking a point here that is so close to 2. X is so close to 2, but it's not 2. Right. In other words, if you look into this function here, this function is the same as the limit as x is equal to approaches 2 of x minus 2. If I'm factorizing this whole thing, is x minus 2 and x plus 2. And then this whole thing divided by x minus 2. At x is equal to 2, this whole thing is undefined. But at any point that is so close to 2, not 2, this whole function will be defined, because x is not going to be 2, but it's going to be so close. So it is okay to cancel out this portion here close to 2, but not at 2. So this is going to be the same as the limit as x approaches 2 of x plus a 2. Now, if you look into this function here, this function is so defined everywhere, even at 2, so this one is defined everywhere. So when I am picking a point that is so close to 2, such that the computer is not going to pick a difference. Let's say I am picking a point, x is equal to 2,00000000000000000000000000001. So when I'm punching that in a calculator, the calculator will get tired and take that value and round it off to 2. So whatever I will be plugging in a calculator, I will end up plugging the 2, because the computer can't pick out the difference. It thinks that number is 2. So I'm plugging in here that number that the computer is going to pick out as 2 plus 2. So this is going to be a 4. So that's how we end up solving this nice example here. First, this x is not the same as 2. I factor out, cancel this thing that is going to give me a problem. And then when I'm taking a value that is so close that the computer cannot pick, of course, when I'm plugging in, I need a calculator to do that. But the calculator, that value will say that value is actually 2. So it's going to plug in 2. So I'm plugging a 2 here so that I get something that is close to this. So this is actually the slope of the tangent line that is touching this curve at this point. Let's look at another example and see, maybe we will get something here. Now, a car's position as t in meters after t seconds is given by s of t is equal to 5t squared minus 2t plus a 3. Find the speed of the car after 2 seconds. Okay, let's talk about the speed. The speed is in meters per second, which means it is actually the rate of change of this function here at t is equal to 2. So we're looking for the rate of change of this function at t is equal to 2. Speed is the rate of change of that. B, find the average speed of the car between t is equal to 1 and t is equal to 2. I want you to see the difference between these two questions here. The first one is looking at the exact speed at t is equal to 2. The second one wanted to see the average between t is equal to 1 and t is equal to 2. What this simply means that it might happen that the car was speeding up and then started to see a dog on the road. It has to stop, it has to slow down, and then it had to jump, it has to. So all those things might have happened between t is equal to 1 and t is equal to 2. So we wanted to see if was the car speeding up between these two, or was it slowing down. So we want to find the average. So in this case here, we want to find the gradient of the line that is passing, that is touching the curve at this point and at that point, or is crossing the curve at t is equal to 1 and at t is equal to 2. So I need to find the output of this and the output of that and use those outputs as y1 and y2 and then find that gradient. This one here is saying I will only have 1 point. So if I'm plugging in there, I will have x1 and y1, and that's it. So they are only looking for the instantaneous rate of change. Here is the average rate of change. So let's deal with these problems here. So what are we looking for in A? We have our ST, which is equal to 5t squared minus 2t plus 3 at some point P, but now we're given that point, the t value, the x value is 2. The output is not given, so I'm gonna plug in a 2 here. So I'll end up having a 5 and a 2, and then I square it up, and then from there I want to say I want minus 2 times 2, because this one is given here, and then I have a plus 3 here. So I have a 19. So here actually we have a 19. So you take this, plug it here, you get an output. So when you are given 1 point, only 1 point, we know that to find the slope of that tangent line, we need the limit as x approaches a. A is the x value here, which is going to be a 2 in this case. And then we need, remember the formula was m is equal to the limit as x approaches a of f of x minus f of a all over x minus a. So here we will end up having f of x is the same as this s of t, so we'll end up having 5t squared minus 2t plus a 3 minus f of a minus f of a here is going to be our 19, and then you divide this whole thing by x, but in this case we will end up having a t because we don't have x, we have t's. So this one was supposed to be t, and then minus, and then this is going to be our 2 there. Now I have this 2 here, which is that 19 is there, the function is there, and then I divide by t. How do I solve that? I still have the limit as t approaches 2. Here I have 19 and 3. Let me just write this as this minus 2t. 19 and 3 minus 19. 3 minus 19 is supposed to be minus 16. So just to confirm, we have minus 16. And then all over t minus a 2. Now, if let's say now I am actually plugging in this 2 here, this whole thing is going to be undefined. Right, if I'm plugging in a 2 here, this whole thing is going to be undefined. A matter of fact, if I were to plug in a 2 here, what will I end up with? I will end up with 5 times 2, square it up, minus 2, and then you have a 2, and then you minus a 16, So in the numerator here, we end up having a 0, and also here in the 0. So that thing actually is saying you that this is going to be undefined. But looking at t and our original way of actually, or the meaning of this limit, it said that pick a value on the right of t is equal to 2, or on the left of t is equal to 2. But that value must be so close to 2 such that the computer cannot pick the difference, but it's not 2. So which means that the first thing that we need to do here as t approaches 2, let's factorize this and see what we're actually going to gain here. If you look into this function here, how do you end up factorizing this? You look at the factors of this, which is 16 here. The fact there are so many factors of 16, but this should not be hard. It should be easy, because I know that if I'm plugging in a 2 here, I will get a 0. So t is equal to 2 is also a value that makes this equal to 0, or t minus 2 should be one of the factors, because it's making that equal to 0. And then the remaining part is going to be very simple. 5t squared divided by t is supposed to be just 5t, and then minus 16 divided by minus 2 is supposed to be plus an 8. I think so, because if I'm multiplying this and that, I will get 5t squared. If I'm multiplying this and that, I will get minus 10t. If I'm multiplying this and that, I'll get t, so I'll end up having a 2. So this is correct. And then I divide this whole thing by t minus 2. Take note that if I'm plugging in a 2, this is going to be undefined. But when I'm picking a value here that is so close to t, this is going to be defined, which means at that particular point, I don't have a problem. So I can remove the problem here, because the value that I'm picking is not really 2, but it is close to 2. So I end up having 5t plus 8. Now, if you look into this one here, what we're basically saying here is that when I am actually picking this value 2 here, let's say 2,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000, such that that difference between 2 and this value 0,00, and then at the end I'm going to put a 1 or 5. It's still close to 2, but the computer, because it has a limit, it cannot pick out the difference. It's going to round off that number to 2. So because we are in the world of computers and calculators, the value that we end up using the value that our calculators and computers understand, and just plug in the 2 there. So we end up saying 5 times 2 plus an 8. And now we have a nice thing here, which is 10 plus 8, or actually 18, right? So that's how we end up dealing with this nice example here, which is A. The second example was B, saying that you have your S of t, which was equal to 5t squared, and then minus 2t plus a 3. And now we wanted to find actually the average speed between these 2 points. The average speed is always y2 minus y1 divided by x2 minus x1. And the points we're given here, we're given the first point here as t is equal to 1. If I'm plugging in a 1 here, I will have 5 minus 2, which is 3 plus 3, so I'll end up having a 6. Just to confirm, this is going to be 1, this is going to be 1, 5 minus 2 is 3, 3 plus 3 is 6. And then the second point was given, we're given t is equal to 2. So if I'm plugging in a 2 here, I can just come here and say I want a plus 3 here. The other point was we're given this point and that point, so to find the outputs, you plug it in here. So we ended up having a 19. So how do you find the average speed between these 2 points? All you need to do, your y2 is going to be 19, your y1 is going to be a 6, divide this by a 2 here, and then x1 is going to be a 1. So 19 minus a 6 is going to be a 13 over 1, which is just 13 meters per second. So that's the average speed between these 2 points. This one is the exact speed, meters per second. Right. So that's how we solved that particular problem. Now, let's take the one last example and then we can call this a day. But before we do that, I want to mention something here. Just a quick summary. So, for average rate of change, our M is going to be, we always have this formula, we always use it, divided by x2 minus x1. And looking for the average rate of change given 1 point. This one is when given 1 point. No, when given 2 points. This is like this. Or I can say this is going to be f of x2 minus f of x1 all over x2 minus x1. So this formula, you use it, or you can use this one, is still going to give you the same thing. Under the assumption that these two equations here are saying that you are given 2 points. So you are given 2 points. It's either you are given here, if you are given 2 points on the graph, like the coordinates, you use this. If you are given x1 and x2 and the function, you can always plug in this value here and get the output, plug in the value here, get the output, and have 2 points. So you use this or that if you are given 2 points. This one is when you are given two x's, but the y's are not given. This one is when you are on the curve. And then, of course, this one is the average rate of change between 2 points, between given 2 points, 2 points. And then now, when you are given 1 point, so all you need to know is that this one is going to be the limit as x approaches a of f of x minus f of a all over x minus a. So you use this one if you are given 1 point, right? So you end up using this one here. What is important about this definition here is that this one is the one we usually call it instantaneous rate of change, or it is the rate of change at point x is equal to a. So it is the rate of change at that point. It is the exact, but this one is the average between 2 points. This one is the instantaneous, or we usually call it, this one is the slope of the tangent line touching the curve at point x is equal to, let me put it like that, at point a f of a. So it is touching the curve only at that point. So we have that 1 point, this one given 2 points, given 2 points x and y, and then here you are given only the x's, x values, and the y values are not given, but you can find it on the function. Now, this one here is another definition that is usually confused with another definition that we will talk about when we are actually at the right time to deal with it, which is saying I have the limit as h approaches 0 of f of x plus h minus f of x all over h. So we have a formula like this, and usually this one we usually call it the first principle. We will deal with it later for now, focus on this. In matter of fact, we can use this definition to derive this one here. This one is called first principle. I think you will deal with it in the course at a later stage. For now, focus on this as the slope of the tangent line, which is also the same as that. But for now, I want you to focus on this. Now, let's take another example here. The last one. Given the function, this is the function, find the average rate of change of the tangent line. So I want you to take note of this. Find the average rate of change of the tangent line. Touching the curve at this point here. You are given 1 point and they're saying average. So it is the average of that tangent line, but it's not the average of this function here. According to this function, what we are trying to find, we want to find the exact rate of change at this point. But for the tangent line, it is the average. So this question here that's saying find the instantaneous rate of f at this point is the same as saying approximate the rate of change of f at x is equal to 1. So these three questions are just one and the same thing. So I want you to take note of this. Look into this question here. Find the average speed. You were given these 2 points. Find the average. Find the speed of the car. The speed is just the instantaneous rate of change of this function. It is the average of the tangent line touching this curve only at t is equal to 2. So take those notes and make sure that you understand so that you don't invest so much only to struggle in the exam. So that's what I want you to do here. So let me just put this aside and actually solve it here. So if you look here, of course, this is our solution, the last solution here. So you were given f of x, which was x cubed, and then minus 6x squared plus 9x plus a 4. And then you were given that I have a point here, which is x. X is equal to 1, so it was given. The output was not given, which means I take this one, I plug it here. This here is minus, right? So I plug a 1 here, so I will get a 1 minus 6, which is going to be minus 5. Minus 5 plus 9 is going to be 4. 4 plus 4 is going to be 8. Let me just confirm here. I have 1 minus 6 plus 9 plus a 4. So I end up having an 8. So this is the point that is given here. I'm going to call it P. Find the instantaneous. Of course, you know that given 1 point and the function, that rate of change is going to be the limit as x approaches a of f of x. Take the function as it is, don't make it harder than it is, plus 9x plus a 4. Subtract the output here, which is 8. Divide this whole thing by, this is just going to be x here. And then here is going to be this input here, which is 1. 8 and 1, function and the variable. So that's how you deal with this. You have the limit. Instead of a, actually this is about to be 1. The limit as x approaches 1. Let's look into this. If I were to plug in 1 here, if I plug in a 1, I will end up getting a 0 in the numerator. Plug in a 1, I will get a 0. 0 over 0, which means that this is going to be undefined. But take note of this. This thing here, this is saying I want to pick a value x such that x is so close to 1, but it's not 1. And also that value, I want to make sure that even a computer cannot pick it up. That is different from this one. So basically, I can proceed and say I have x cubed minus 6x squared plus 9x. 4 minus 8 is going to be minus 4 all over x minus 1. I want to factorize this. Why am I factorizing it? It's because once I factorize it, there is a high chance that I can cancel the problem. So here I will end up having the limit as x approaches 1 of, because this one is the reason, x is equal to 1 is the reason that this is going to be equal to 0. One of the factors must be x. Change the sign of this, so because it's positive, it's going to be minus. Now I need to know what is inside here, and then all over x minus 1. This is not hard to figure out what is here. So what you do, when x is equal to 1, this whole thing here, this whole thing is going to be equal to 0. So I will end up having, I'm going to take in the coefficients here, 1, 1, minus 6, 9, positive 9, and minus a 4. And then this x is equal to 1 is the one that is making this whole thing equal to 0. And then I'm going to use long division. This one, you drop it as it is, and then after that you multiply this with that, you place it here, you get a 1. You add this and that, you get a minus 5. Minus 5 times 1 is minus 5. Minus 5 plus 9 is positive 4. Positive 4 times 1, you get a positive 4. Positive 4 and minus 4, you get a 0. Which means that whatever is supposed to be inside here, because I've reduced this by 1, this must be a quadratic. So I have 1x squared minus 5x plus 4. So that's how this thing is actually do. When I'm picking a value x that is so close to 1, this is not going to be a problem because these values, x is not equal to 1. So I can cancel it out. And then I'm left with x squared minus 5x plus a 4. And if you look carefully into this value here, x is closer to 2. I mean closer to 1. Like it can be 1,000,000,000,000,000,000,1. But when I'm plugging it here, that value, the calculator cannot deal with that value. So it's going to round it off as 1. So calculator-wise and computer-wise, I will end up having to just plug in that value if I want to calculate using a calculator. So I'll end up having 1 squared minus 5 times 1 plus a 4. So this is going to be 1 minus 5 plus a 4, which is 1 minus 5 is going to be minus 4, so it's just a 0. So the rate of change at this particular of this curve here is just saying we have 0. So if it's 0, this actually just means that we have a max or we have a mean. So it is what it is. There's nothing that I can do. And then the second question was approximate, also it was just the same thing. So I'm just gonna stop there, and I want you to just take note that this and this means one thing. It's just one and the same thing, and they can be used interchangeable, but for now we're still dealing with that. Right, that is what is important with this. I think I'm gonna stop in there and see if you can actually try and understand this. Thank you very much.